Introduction. So as Hervé just said, I'm from a lab that is not so much specialized into bioacoustics than rather signal processing and machine learning in general. And we process data, whether it comes from images or from sounds or from text. So these ideas are apply to several problems, but today I will try to explain how they can resonate in the bioacoustic community. And here, well, as you can guess, I'm not too knowledgeable about the subject, so I don't want to impose my own view on the I don't want to impose my model, but I just want to share with you some criteria for assessing the quality of a classification, automatic classification pipeline for bioacoustic data. So I will present a new algorithm that is called multivariate scattering. So everything began with the BirdCLEF challenge that Hervé presented just before. So it's a bird species identification challenge that Hervé proposed to me to try to investigate. It's based only of audio, and it's supported by the University of Toulon, among other faculties. And what really amazed me when I discovered the dataset is its uncanny difficulty. It's very large scale, it's very long. There are about 1,000 of classes, which is in fact only a small subset of the actual biodiversity of South America, and we don't have many examples per class. We have as few as 15 examples per class, so that's real world, of course, but that's a big problem for example-based machine learning. And obviously annotation is made by hand, so we are not we are maybe exposed to mislabelings and so forth. However, in spite of this frightening difficulty, for the more heartwarming part of it is that it's a really good benchmark for digital signal processing tools, because as you all know, bird sounds epitomize the concept of transient, because they change pitch very sharply, very rapidly. We know the species, so we know, well, we can study the acoustic model, we can study the production model, so rely the physics of the data with the signal, so that is of course very appealing. We have a broad range of recording conditions. There are thousands of different recordists, so it's the data is somehow statistically decorrelated. At least we are not too much overfitting the recordist or the recording condition, so it can be a robust evaluation. And finally, we can study the impact of noise, or at the largest extent, the impact of background species on the classification. So now, what do we do? Once we have these 300 hours of data, we have these labels. How to generalize from these examples. So I will propose four ways to go that go from the more general to the more specific. Well, the first way to go is just to define the problem as a classification problem, like any other. Well, we have signals, call them X, and we are trying to discriminate them into different classes, say class K against class L. And in machine learning, there is it's very easy to solve that problem with examples as soon as the data are already linearly separable. If they live in a space where we can build a hyperplane to separate the two classes, well, your problem is almost solved. Of course, that's not the case. That's not the case. There's no reason why the audio samples should be linearly separable in the raw data domain. So the art, or the whole deal now is to find a nonlinear function, call it x, s of x, that will bring the signal to a domain where the classes pairwise become linearly separable. So we are trying to find, if you like, a similarity measure, Sx, Sy, and a product between the two. And well, that's just the definition. We haven't gone too far. And so now, what constraints can we put on S? Well, sparsity is a nice constraint, and it's specifically adapted to birds. Yeah, in fact, the study of the bird vocabulary is older than the idea behind compressed sensing and sparse coding. But if you look at a European bird, since as skylark, Alouette des Champs, even a 10-second sample can be segmented in meaningful ways. So let's try to listen to it. D, E. This is a hand annotation, but as you can see, it's already very rich on such a short sample. And this is likely to tell us a lot about the distribution of the data and the species itself. And by the way, it goes much further than just finding the species. It's really a nephrological problem of analyzing its behavior. So somehow adapting the representation to the vocabulary is the way to go. So how to adapt? The bird songs are consistent multiple scales of, if like, coherence, or multiple scales of that we can integrate. So instead of going from the very small scale of the short samples to the scale of the song, the deep learning way would be to perform linear operations, such as convolutions, in the time-frequency domain, and iterate on them, cascade on them, over longer and longer time scales, until we reach an abstract level that is the species. Each unit here, hopefully, will react as a spike to the unit. So that would be the dream. So, well, we still don't know how how to train these convolutional layers, but I will try to show today that at least we have insights on the very first layers of operation. We can specify what we want quite explicitly. But the idea behind deep learning that I like here is that we progressively gain access to abstract concepts by integrating over longer time scales, and this will recur in my talk. And finally, at the most fundamental level, the study of the bird calls is a signal processing problem. It's about studying a dynamical system. If you, well, quite broadly, if you model the bird as a behavior of pitches and amplitudes, which are regular functions of time, as inputs to a time invariant system that is the body of the bird, then both these parts provide information to you about the species. So it's a somehow inverse problem where we have to find these parameters, these functions of interest from the signal, and in the signal, obviously, all of these are entangled in some non-trivial way. So to find out this idea, I can provide you the example of the common redstart, which makes these bird calls. Listen. So there are changes in inter-onset intervals and in chirp slope and so forth, but we kind of find that all of these proceed from the same system up to small deformations of the behavior. So we have to disentangle these factors of variability and analyze the problem. So to recap this small prelude, we have these, say, 4 paradigms. Kernel learning way, right? It's all about discriminating classes, so finding a good discriminating measure, similarity measure. Then we have the sparse way, sparse paradigm that would say, oh, it's all about vocabularies, it's all about finding a good dictionary, but then on top of what? On top of maybe a deep learning architecture that would going for the more fundamental small-scale features to the more abstract concepts. And finally, in the end, it's a signal processing problem about modeling distribution of the data. So, apropos of this data distribution, of course, to me the biggest pitfall in this BirdCLEF dataset is the intra-class variability, which is tremendous. Now, part of, I won't make you listen to all of these, but these are the recordings of the same species, the flycatcher, from the same person at the same location over several years, but sometimes they are even the same individuals. So it's really about the behavior here, and as we can see, there is a big difference in spectrograms between this shape and that shape. So that's a behavioral intra-class variability that we cannot put in the model itself. However, if you look at these patterns, they recur of different examples, but they do not recur as carbon copies. They recur up to deformations. They recur up to frequency translations, drifts, rhythmic drifts, and all of that. And so that's geometric variability, if you want, and that can be put in the processing pipeline quite efficient, quite simply. So so we want to learn this kind of geometric variability and find the relationships between those time frequency patches. So what's at stake in geometric variability? Well, we might say that if you call that x of t, this small patch, does this other patch, can this other patch be somehow produced from the original up to a deformation? So a deformation in math or in physics would be a smooth time delay function. It's a change of tape speed, if you like. So you replace the x of t by the x tau of t, where tau of t would be the diffeomorphism of time. So for which tau does x tau sound similar to x? Well, for small tau, obviously. But what is small tau? Well, there are two orthogonal questions. One of them is translation, because in the previous slide, as you can see, the t equals 0 axis doesn't mean anything really. These translations are completely arbitrary. And the other will be the time drift itself and the actual small deformation. So let's start with invariance to translation. That's the tau of t equals a constant. And of course we want to kill that part of the variability. So we require translation invariance up to some large c, maybe 1 second, but obviously we want the c as large as possible. So s of x equals s of xc. In the frequency domain, that would mean that the representation should not carry any frequencies above 1 over c. So it should be very regular. So if you have an irregular description, u of x, well, that's fine, but you will always have to low-pass filter it in order to keep only the regular part, like so. You keep only the the low frequency part of U, and well, the difference between the blue line and the green line, which are translated one to the other, are now small. So the low-pass filter does the job, but of course that's not the end of the story, because we have lost a great deal of informative discriminability while going from here to there, obviously. So that's for invariance. Now to stability. Well, we can specify a norm for tau, which is, if you bear with me, the maximum of the derivative of tau, so the maximum amount of deformation. So the change in representation, the change between S of x and S of x tau in Euclidean norm, should be of the order of the maximal amount of deformations in time. So that's a Lipschitz inequality, only for small time warps. And that's pretty natural, because in classification this will mean that all the green rectangles that I showed you previously will somehow belong to a linear subspace of the original example. So that's quite attractive. Note here that Fourier spectrum, taking the modulus of the Fourier transform, although is invariant and discriminative, is not at all stable, especially in high frequencies. Think of a sound that has 6 different partials. If you move the first partial by, say, 1 Hertz, well, that's not a big deal between the two. But the 6th partial will move by 6 Hertz. So these two won't overlap at all. So the Euclidean distance in the Fourier domain would be very big. So Fourier spectrum is fine for visual check, but if you have large harmonic structures in your data, I would advise against having a linear frequency axis and instead having a logarithmic frequency axis. So how do we achieve this logarithmic frequency axis? Well, by resorting to wavelets. We can have elongated structures in the over the frequency axis and trade this loss of frequency resolution for gain in time resolution. So what is a wavelet? Well, a wavelet is an oscillating localized filter, like so. And a filter bank of wavelets is built by dilating one single, say, mother wavelet, a mother shape, by different factors, lambda 1, that may be big or small, and these will shrink you or dilate you the shape of the wavelet, so that will change the center of frequency and that will change the time support as well. And here, a technical property that is very important for what's coming next is analyticity of the wavelet. That is, no negative frequencies. So, or in other words, the real part of it's a complex function. So the real part and the imaginary part are in phase quadrature of each other. So there's blue and green here, and the red is the envelope. And as you can see, quite obviously, although the blue and red line will somehow match the typical oscillations in your data because it's vibrating, once you apply the modulus to it, well, it has a nice smooth shape. So you regularize, you give regularity to the wavelet transform. So that's much more regular. So that's better for averaging afterwards. And this, unlike the Fourier spectrum, this approach is stable to deformations because a small time warp of the signal can be induced as a time warp of the wavelet itself instead. So the neighbor of the wavelet is another wavelet, so that's perfectly fine. Up to a change of variable, that's okay. So in the Fourier domain, the wavelet, the dilated wavelets yield a nice filter bank that resembles much what we have in our cochlea. And we do so for exponential values of the center frequency. This is the center frequency, so that would be somehow the resolution of the log frequency. And in order to have perfect energy conservation and to not lose information, we put our low-pass filter here. So the wavelet transform consists in it has two outputs. One of it is the band-pass, all the band-pass outputs of all these band-pass filters, the wavelets, and it has this invariant representation, which is the low-pass part that you have specified with your C time invariant scale. So let's look at this. Well, you might know that fairly well. It's a time frequency representation, except that this gamma here is the log of the frequency. But we are all accustomed to that. And obviously, the original signal was very oscillating, and here we see nice regular lines, so that could be averaged afterwards. So we define the wavelet modulus, U1 of x, as well, the modulus of the convolution between the signal and all these wavelets indexed by gamma. And this is stable, it's regular, it's sparse. Well, it's not invariant. If you wanted invariance up to the whole length of the signal, which is realistic because that's what you want if you want to identify the species, that's not enough, unfortunately. So we put another averaging to it. So after taking the wavelet modulus, low-pass filter again, and we call that the S1. And S1 would be the averaged wavelet modulus, and that's essentially a constant Q spectrum. So it's a constant Q transform. And the constant Q transform has a very nice property. It has the amount of invariance we wanted, it has stability, and it's somewhat discriminative of the different musical notes. So that's fine. However, if you increase C beyond 100 milliseconds, well, you lose all the non-regular information, and all the notes here are blurred into one. And obviously that's not what you want. If you have several species singing together, you don't want to merge them together. Obviously, you want to melt your information into a single vector. So what can we do? Let's recap. So we had our signal. It's obviously discriminative, but it's not regular and it's not invariant. What we did was that we increased the regularity by applying analytic wavelet modulus, but that is not invariant neither. And we had this invariant part, which is the DC component. So that's a general idea, but the DC component of the bioacoustic signal does not tell you anything about the species, it tells you something about the device. So you throw that out, it's not informative. So all we can rely on, after all, is that, the constant Q spectrum. So what is the constant Q spectrum? It's the outcome of two operations, one to regularize wavelet modulus, and one to average and bring invariance, low-pass filter. Well, but if we look at this in this 2D way, we say, oh, but here, we are pretty much in the same situation as here, right? After all, what we want is to increase regularity, again, because we want more and more regularity and increasing over bigger time scales, and then averaging. So let's iterate that process. This process of time frequency representation maybe is just the first step of a cascade. So here we go to the meat. The idea is to scatter the signal again, to do a wavelet transform of the wavelet transform modulus. So wavelet transform is linear, but then the modulus is nonlinear. So that's a convolution and a nonlinearity. And again, a convolution and a nonlinearity. So that's pretty much the architecture of a convolution of neural networks layer, except that everything here is handcrafted, nothing is learned. And from these outcomes, call them U1, U2, and so forth, you have your S1, S2, that are the invariant parts of them. So that is up to, say, 1/10 of a second. Now if we increase to 1 second, well, somehow we have lost the distribution here of the notes in this averaged wavelet transform. However, somehow we have recovered the transient information in our S2 signal, which is the amplitude modulation spectrum. It's something that has been studied before. It's not so new. Now, at this stage, you might think that something is wrong here, that I stopped talking about bioacoustics because I showed you musical notes. And that should make you suspect that I've hidden a problem from you, and you would be right, because at constant musical notes have the nice property that they remain constant. They remain, not constant, but they remain at the same frequency for quite an amount of time. And that's not at all suitable for a bioacoustic signal, which has many chirps in it and so forth. So, in fact, this process of filtering a long time and a long time and a long time and applying modulus, well, could be fine for simple structure problems, but texture problem for speech maybe, but certainly not for bioacoustics. So, yes, I talked on this slide actually. This is the formula for what I just defined, and these convolutions are performed a long time, and a low pass a long time. Okay, so we have designed them to be invariant and to be stable, so we have that, that's fine. But they won't be discriminative enough for actual bioacoustic data and bird chirps in particular. So a possible solution to that problem would be to replace the wavelet here, the second order wavelet, which operates only a long time so far, by a time frequency two-dimensional wavelet, which operates a 2D convolution in the constant Q spectrum. So what I will explain next is pretty much unpublished material, so feel free to comment. And okay, it's not at all a set-in-stone theory. My colleague Joachim Anden introduced in his PhD thesis these joint time-scale wavelets. It's just the product of a Gabor wavelet in time, along time axis, and another Gabor wavelet along the log frequency axis. And as much as the 1G wavelet can be dilated over one dimension, you can dilate these in 2 dimensions. You have a vertical degree of liberty and a horizontal degree of liberty, and you may even flip them so that it no longer goes upwards but backwards. So you have these two degrees of liberty, but still that's a two-dimensional frequency. That's perfectly fine and well defined. So how to evaluate this approach as compared to the standard time scattering transform that I've defined so far, that is entering into this is well known, well understood. Well, instead of providing a full-scale classification report, I will just provide you a result that I did actually last week on reconstruction from invariant representation. So if you recall, we had this from X going to U and to U and to U, so that's the wavelet modulus, and after all this stage, this cascade of wavelet modulus, we average all that. Of course, if that was regular, we don't lose much by averaging. If it's not regular, we've lost a lot of information. So the problem here is, given the S and only the S, not the original signal, can you generate an audio surrogate for the signal that would kind of match perceptually what was the original target? So it's about reconstructing signal from an invariant representation. And for that we apply a very baseline technique, iterative gradient descent. It can be expressed in closed form with dual wavelets, so it's completely standard. And what we want here is just to minimize the distance between an S infinite target and the representation we're building. So optimally these could be equal, and then we will have different signals with almost the same representation. So let's listen to some results. I hope you'll be able to listen. I don't have loudspeakers.
You can plug this
Yeah.
in, Jack.
So it's built on an accipiter bird, and here's the original. Is it turned on? Yes. Oh. Oh, sorry. Well, what can I do? Again? Is it? Are you
Yes,
sure it's
it's-
turned on or not? Oh, well, never
do
mind.
yours.
Maybe I'll
Yeah.
put it in a...
Mm.
Okay, so that's the original, the bird chirp. Right, that's pretty typical. Now we impose a C, an average that is 3/8 of a second. That's not a lot there actually, so it could be more difficult. Here is what a well-cited texture synthesis technique provided by McDermott and Simoncelli does from that data. Oh, so we have this amplitude modulation, we have this kind of intermittency, this rhythmicity, but we have lost the chirping structure. Now in the scattering domain, what can we do? In first order, so providing just an averaged constant Q spectrum with no aggregation strategy whatsoever. No transient at all, obviously. If you do this, what I explained, the second order coefficient, so another wavelet modulus on top of the U1, this is what you get. So again, we've restored somehow the rhythmicity, but it's completely decorrelated between frequency channels, so we don't recognize the species at all. You may not recognize it's a bird at all, actually. Now, if you put the joint wavelets on them, and I swear this is not fine-tuned at all, so maybe it could be better, I don't know. This is what we have. So we see that the chirping structure is somewhat restored. Of course, it's not perfect, but perhaps it's more more comparable to the original than the previous reconstruction were. However, a problem here is that we decorrelate the harmonic, the partials, because this is made of partials that are obviously completely synchronous. And this gives local synchronicity for adjacent frequency channels. But it will not synchronize the partials together on a very long range. So how to address this, and I will finish with that. Well, we might recall some old school experimental psychology of circularity and pitch judgment provided by Roger Shepard in the United States and Jean-Claude Risset in France. And he made that interesting experiment. Listen to this sound going from note C2 to 1 octave higher. Oh, I don't have it. Well, but they are in the next thing. So just say that we have two ways, and we'll listen to them afterwards. Two ways going from C2 to C3. One of them would be the staircase, going through all semitones in the octave, and the other would be somehow the lift, not changing the pitch chroma, not changing the pitch name, but just attenuating the odd-numbered partials so that it sounds 1 octave higher progressively without circulating at all. So let's listen to that in a visualization that is a spiral frequency axis, which does 1 turn per octave. Then the staircase way would be a full turn, and the lift would be a change in radial change. Let's listen to the chirp, the staircase way from C2 to C3 on the video. So that's a full turn. Now, a radial motion in the spiral would be a change in octave, a change in timbre and formantic structure would be like that. So no rotation whatsoever. It's merely a local change, but along the radius axis, the radial axis, not on the angular axis. So this is merely a reconfiguration of the frequency axis. It's no longer rectilinear. It's enrolled in a spiral, such that we have here two phenomena that can be somewhat disentangled. One of them is the rotation, and the other would be the dilation. Coming back to the birds, in South America, there is this crested guan bird which has this amazing song or call that changes at the same time the pitch. As you can see, it goes upwards, and partials appear, so the timbre is getting brighter and brighter, and the amplitude changes as well. So all three parameters change, and then it finishes by a burst of white noise. So maybe if we look at that in the spiral over several repetitions, you'll find all of these. Well, it's very fast actually, but it's the slowest bird I've found. And you will see the rotation behavior, the rotating behavior, the dilating behavior, and the burst of white noise that completely fills the spiral with grayscale. Let's listen to that. So is it okay? Is it okay? Do you see my point? Or it's the ascending chirp rotates along the center, and then the change in formantic structure is illustrated by the fact that it's getting further and further from the center, so it's brighter. This is just an amateur script that I've written, but this will soon be launched on a more professional level by Thomas Eli from IRCAM, who's made a real-time plugin that illustrates that with beautiful colors. It's much more compelling than what I can provide here. So again, going from the standard plane wavelets to the joint wavelets to now the spiral wavelet, we have not discovered, but we have highlighted a third dimension that is not rectilinear pitch, it's not time, it's rather the octave index. So, well, canonically we can define a spiral wavelet as a tensor product of these three. So we have a gamma tone here oscillating along time. We have a Normale oscillating along chromas, giving this pitch drift. And we have this harmonic contour that changes. And since it's a product of wavelets, since all the filter banks are unitary, the theory remains the same. It's a more complex object, but it's made of three simple objects. So we can keep exactly the same formalism. So this is what the spiral wavelets look like after you've unrolled them in the classical time log frequency domain. Now we have 3 degrees of liberty, not 2. We can dilate them along time, along chromas, and they have this harmonic decay that can be like, here is 2 octaves, here is twice that, so 4 octaves, and it can go upwards, downwards, in frequency, in chroma, in octaves. So we have many degrees of freedom, but that's fine. It's a unitary filter banks of representation. So this is what I've come to after this 1.5 years of PhD, and I can say that, well, it's a proposal for what could be a signal processing informed second layer on top of the scalogram as a convolutional layer. So to conclude, I'd say that BirdCLEF is all about disentangling variability. Of course, noise and background species and all of that make the problem even harder. But if you put all these birds in an anechoic chamber, it would be almost as hard, I would say. So it's really about the behavior of the bird that we have to model. I've shown these three simple criteria: invariance, stability, discriminability. It's very easy to have two of these three, but to have all three is really tricky. But well, the scattering cascades kind of gains access to all these three on bigger and bigger scales. And I've presented for this talk the joint coefficients and the spiral coefficients that maybe can model better bioacoustic data. So now what will follow, because I'm only at the start of my studies, I will investigate on spiral-based now invariant analysis synthesis to see if it improves or not. I hope so. And of course, put this into an actual classification pipeline and see the results. Thank you.
Yes, very interesting, thank you. I'd like to see results on compared with other, like you showed more results for the same kind of sound types. It would be very interesting to see different sound types, but the question itself, it's not this was just a comment. How computationally expensive is that technique?
It's faster than real time.
Okay. This is good for the classification
Yeah.
part.
It's faster than real time. It's not easy. Actually, the algorithm is simple. It's just 3 convolutions. But then making it faster than real time requires a bit of know-how about memory allocation and fast convolutions. That's all. There's nothing too difficult. And it can be parallelized, of course. It has these frequency channels which in time scales which are independent. So it's embarrassingly parallel. Yes, sir?
I think you're worrying too much about the Fourier transform artifact, because most of those harmonics are not there. We gave up on the Fourier transform about 8 years ago, and we're using the LBC, and with that, about 80% of the harmonics disappear. They're just not there. If you filter them out, they're not there either. So you can filter it first, have a look, and then do the FFT afterwards, and you'll find that they're not there.
Sorry, I have understood the beginning.
The harmonics.
Yes?
They're not there. Most of them are not there.
Yeah, for birds. Because
for birds, particularly for birds, yeah. Some of them are. Some birds generate harmonics on purpose, but the FFT generates a lot more harmonics than are there in the first place. So you're actually chasing the FFT around rather than chasing the bird.
Okay, I see your point. Yes, it's true that in the past specific case of birds, we can keep that because a model of sinusoid with instantaneous frequency that is varying is fine. But then for deers, can you do that? I'm not sure. Yes.
The question from the first works about the scattering transform, when your second layer is only convolved with only over time, after the joint is integrating ortho versus frequency, and now you're integrating the third dimension, if I understood correctly. Do you think you will have to go to the fourth, fifth one in order to capture most of your invariants?
I think now we have to go nonlinear after that.
Okay.
So 3 variables at the second layer. Well, of course, you'll have to trust me. Is the maximum we can do. So it is really interesting to do. So after that, if you want to study, say, musical structures or rhythmic structures, put a modulus to demodulate all that. So you will have access to sonic units, and maybe make another transform along time as a third layer, and perhaps along other variables. It may be the gamma 2 variable, the modulation amplitude, because it's kind of a tempo variable, and it also has a spiral structure actually. So maybe this is even can be iterated again. The spiral itself is not limited to acoustics, in fact. Yes.
I got a second question related to the deep learning. Well, I have been shown rhythmically that, for example, to the winner of different computer vision challenges, show that for the first layers they didn't perform any pooling. So they bypass and then introduce pooling factors from the second layer and so on, for example. I don't know why, but do you think you should avoid, for example, your first low-pass filter or the first layers and maybe introduce later your...
No, there's no choice. The low point.
Yeah.
In this construction, the low pass filter has to be there to fill the filter bank. You have a finite number of wavelets. You cannot go up to down to 0. At the limit, you have only a Dirac in frequency, so that is a full integration. Fine, but you are constrained to doing at some sense. But it's not pooling; it's averaging, so it's linear.
Yeah.
Perhaps you can do also transformations of the S1. That's not our formalism, but why not? Actually.
Okay. So thank you very much.
You're welcome. Thank you for your attention.
There will be time for other questions in
Okay.
the lunchtime.
Thanks
So we turn.